Good evening, students. So yesterday we were discussing some important topics, right? What were they? We started with refraction. Am I right?
Yes.
So in refraction, till where did we discuss?
Laws of refraction.
Yeah. We saw what will happen when light travels from one medium to another, right? So what happens when it travels from a denser to rarer medium and rarer to denser medium? Okay. So listen, if I take a boundary like this, okay, which separates denser and rarer. Okay. So let's consider a ray hitting the boundary and the ray is traveling from denser to rarer. So if I draw the normal at this point, if I take this as the angle of incidence, then how will the angle of refraction in the second medium be? It will be a value greater than the angle of incidence. So the ray will bend away from the normal. Right. If I call this as I1, this will be R1. Now what will happen if I increase the angle of incidence to I2? What will happen to the angle of refraction? It will also get increased to R2. Now, what if I increase the angle of incidence even more? Let's say it is at a value of I3. Then the angle of refraction will become R3. Correct? Right. So this keeps on going. Then there will be one particular angle of incidence. There will be one particular angle of incidence for which the refracted ray will be like this. Accepted? So this angle of incidence for which the angle of refraction is 90 degrees. So this kind of a movement is called as grazing along the boundary. Okay. It's called as grazing along the boundary. So the angle of incidence for which the ray refracts exactly along the boundary is what is called as critical angle. Are you able to understand? So this is what we call it as critical angle. So what do you think will happen if I increase the angle of incidence beyond this value?
So it will get reflected back.
Perfect. So this is denser, this is rarer. Okay. So if I increase the angle beyond this value, then the ray will get reflected back into the same medium, though it has a feasibility to travel into the other medium. And this kind of a phenomenon is called as, any idea?
Total internal reflection.
That's right. This kind of a phenomenon is called as total internal reflection. Okay. So this phenomenon of total internal reflection can be observed only when the light ray is traveling from denser to rarer medium. The vice versa, it will not work. Okay. Now listen to this carefully. If I have to define critical angle, how will you define it? So what is critical angle? It is the angle of incidence. It is angle of incidence in which medium? It is angle of incidence in which medium? In
denser medium.
In denser medium, for which angle of refraction is how much? Is for which the angle of refraction is how much? Is 90 degrees. Is what we call it as critical angle. Okay. So if I take the refractive index of this medium as mu1, refractive index of the rarer medium as mu2, listen to this carefully again. Mu1 into sine C is equal to mu2 into sine of how much? 90. So mu1 sine C will be equal to mu2, which implies sine C will be equal to mu2 divided by mu1. So C will be how much? Sine inverse of 2 divided by. Okay. So C will be equal to sine inverse of mu2 divided by mu1. If mu2 is equal to 1 and mu1 is taken as mu, then C will be equal to sine inverse of 1 divided by mu. Okay, so you can either have this as an expression for critical angle or you can derive it also based on the problem. Next. So what is total internal reflection? It is a phenomenon.
Phenomenon. Light gets reflected back after hitting.
Yes. Can I say bending back into the denser medium? And when will this happen? When the angle of incidence
Greater than the critical angle.
is greater than the critical angle. The angle of incidence is greater than the critical angle. So this is a phenomenon. Okay. So that's it about the total internal reflection and critical angle. So there is the application of total internal reflection that is there in the textbook. So this part I'm again giving it as self-study. One is mirage and the second is optical fiber. Okay, the remaining also you can study, you can go through it, and if you have any doubt, reach out. These are all theoretical parts. So if you understand what is the total internal reflection, you will be able to understand these concepts. So to get more grip over this, I'll be solving some problems today. Okay. So first set is we'll be solving problems based on refractive index and apparent shift. That's it. First, let's solve them. So let's take this. So there is a ray of light of frequency 5 into 10 power 4 hertz, which is passed through a liquid. So the wavelength of light measured inside the liquid is found to be 450 into 10 power minus 9 meter. Calculate the refractive index of the liquid. So how to solve this? So what is the formula for refractive index? Refractive index is equal to speed of light in vacuum divided by the speed of light in medium. So this will be 3 into 10 power 8 divided by what will we get at the bottom? The speed of the light in the given medium. So how can you write speed in terms of wavelength and frequency?
Wavelength into frequency, right?
So lambda into f. So multiply those two values and calculate. Tell me what you're getting. Do it fast settle. What are you, what are you getting? Okay, that part you do it later. Do the second one. There is a light of wavelength 6000 angstrom in air, enters a medium with refractive index of 1.5. What will be the wavelength of light in that medium? How to do this?
So we have the refractive index. So we should first find the velocity of light in that medium using the refractive
Actually,
index.
velocity is not needed. You need not find the velocity. There is a formula that gives you the relation between refractive index and wavelength. I told you an important point yesterday. What did I say? Oh, I didn't tell you. Huh? Okay, write it down. See, we know that V is equal to lambda into F. Correct? Huh? So can I write this as lambda 1 into F divided by lambda into F? If you observe, I didn't write it as F1 and F2 because the frequency of the wave in both the medium will be the same. I reiterate, frequency of a light traveling in two different medium will be the same because frequency is the characteristic of a source. So whatever is the desired frequency, if you put that source into that amount of vibration, you will get that frequency. So F and F will get cancelled. It will be lambda 1 divided by lambda 2. Okay. Now you have a ready-made formula. Apply this and tell me what is the answer.
So it will be 6000 by 1.5. So we get 4.
So 6000 divided by 1.5. 1.5 you can write it as 3 by 2. So this will give you 2000 into 2, that is 4000 angstrom. Okay. So similarly, try the third one. Others are sleeping, huh? Guys, this is a serious and a last warning. If you're not going to speak, I'll push everybody out of this class. I'll leave only the person who was talking to me in this class. This is the last warning. I'll give you exactly 5 minutes time. Okay, if you guys are not going to open your mouth and speak, better be out of the class. Yeah, Niklesh, please tell me that. The refractive index of
Sir, can you repeat that sum again?
why are you asking now? When I'm asking
Sir,
100 times to people, is
Sir,
it not
I was
based?
about to ask you a few minutes
You can
back.
ask. mu21 is equal to lambda 1 by lambda 2. Mu21 they've given it as 1.5. So 1.5 is equal to lambda 1 is 6000 divided by lambda 2. Lambda 2 will be equal to how much? 6000 divided by 1.5. That is why we got 4000.
Okay, sir, understood.
So what is the answer for third one? Hemant?
They're doing, sir.
How to do? Tell me the formula. It's one step problem. Tell me what is the formula. So what is given in the question? Refractive index of glass is 1.5. Refractive index of water is 1.3. If the speed of light in water is 2.25, then what is the speed of light in glass? How to do this?
We can directly do that without considering the speed of light in water.
So refractive index of glass by refractive index.
What?
Refractive index
Sir,
of glass by
speed-
refractive index of what? Sorry?
So we can do it like a speed
I
of
told what?
light into refractive index of water by refractive index of glass gives a speed of light in glass. Sir.
Yeah, that's right. So they are inversely proportional. No, refractive index of glass is 1.5. Refractive index of water is 1.3. Will be equal to speed of light in water is going to be 2.25 into 10 power 8 divided by speed of light in glass will be Vg. One unknown, one equation. Right. I hope you guys can solve this.
So I'm getting 2.92 for speed of light. So
2.92. You should get a lesser value.
So I
2.25.
got the answer as 1.95 itself, sir.
so even I got 1.95 into 10 to the power 8, sir.
Yeah,
But
this is the answer. But what is the problem? See,
I know, sir.
actually, this will go 1.5 times. 1.5 to 1.3 will give you the answer. 15/13 is how much, sir? Is it 195?
Yes, sir. 195, sir.
So then it should be 1.95 into 10 power 8. So what exactly happened? What is your doubt? What is your doubt? Am I clear or not?
Yes, sir. But the speed of light in vacuum I'm getting is 2.92, sir.
No, no.
You have
Speed of
written
light.
2.25.
They
So,
have given the speed of light in water is given. Why are you finding it again? I use the formula of relative refractive index.
Oh, okay, sorry, sir.
Okay. Four. So there is a ray of light that passes through a plane boundary separating two media whose refractive indices are 3/2 and 4/3. Let's try to draw a diagram and see. So there is a boundary which is separating two media, which is 3/2 and 4/3. If the ray travels from medium 1 to medium 2 at an angle of incidence 30 degrees, what is the angle of refraction? So it is traveling from medium 1 to medium 2. The angle of incidence here is 30 degrees. R is equal to what? So how to solve this? Mu1 into sine 30 degrees is equal to mu2 into sine r. So mu1 is how much? 3/2 into sine 30 is half is equal to mu2 is 4/3 into sine r. So sine r will be equal to 9 divided by 16. R will be equal to sine inverse of 9 divided by 16. Okay, sine inverse of 9 divided by 16 will be the answer. If the ray travels from medium 2 to medium 1 at the same angle of incidence, what is the angle of refraction? Calculate it again.
Sir, sin r is equal to 4/9.
4/9. Huh?
Yes, sir.
So you will get mu2 into sine 30 degrees is equal to mu1 into sine r. Mu2 is how much? 4/3. Sine 30 is half. Mu1 is 3/2. Did you? How much did you say? 4/9. Huh?
Yes, sir.
Correct. Correct. So sine r is equal to 4/9. So r is equal to sine inverse of 4. Correct. The glass prism. We have to. Okay, now I'll explain the concept of glass prism. So write it down. Refraction of light through a glass slab. When I say glass slab, I'm talking about a rectangular glass slab. Okay. So listen. If there is a glass slab like this, and the ray is hitting the surface at this point. So if this is the point of incidence, at this point of incidence, draw a normal, and this will be the angle of incidence. Right? So outside medium's refractive index is 1. Inside it is glass. I will call the refractive index as mu. Okay. Then when the light is traveling from rarer to denser medium, what will happen?
towards
Right.
normal.
So it bends towards the normal. Now this refracted ray will start acting as the incident ray for the second surface. Now what will happen at this point? ray is traveling from denser to rarer. So it will travel away. So that the first ray, whatever is there, is called as the incident ray. This is called as the refracted ray, and this is called as the emergent ray. Okay. Now listen to this carefully. This angle is called R1. And this angle is called R2. And this angle is called angle of emergence. Okay. So mu1 multiplied with sine I will be equal to mu into sine of R1 when I apply Snell's law at point A. Accepted? Similarly, mu into sine R2 when I apply the Snell's law at point B, mu into sine of the angle in that medium is equal to mu1 into sine of E. Accepted? Right. But what is the relation between R1 and R2? You have two normals.
R1 is equal to R2.
R1 is equal to R2. If I take and substitute it here, I'll get mu into sine R1 is equal to mu1 into sine E. So if I take this as 1 and this as 2, mu sine R1, mu sine R1. Left hand side is mu1 sine I. Here right hand side is mu1 sine E. So mu1 sine I will be equal to mu1 into sine E. Mu1 and mu1 will get cancelled. Sine I is equal to sine E implies I is equal to E. Clear? So what is that you're able to understand from here? That the incident ray is parallel to the emergent ray. So the important conclusion that we can draw from here is incident ray is parallel to the emergent ray. Okay. And the observation that we can see here is, it is very clear that the incident ray has got displaced, and this distance is called as lateral displacement, which is represented by the symbol delta x. Okay. Lateral displacement, or sometimes it is also called as lateral shift. This is another term that is used. Am I clear, guys?
Yes.
Good. Please write it down.
Yes, sir.
Completed? Okay. Now let's try this problem. So there is a rectangular glass slab which rests in the bottom of a trough of water. A ray of light incident on water surface at an angle of 50 degrees passes through the water into glass. Calculate the angle of refraction in glass, given that mu of water is 4/3 and that for glass is 3 divided by 2. You guys draw the ray diagram and tell me in terms of sign. I don't want it in terms of exact angle. So what is the answer? I asked what is the answer in terms of sine inverse. Huh? Answer? So there is a glass slab. A ray of light is incident on the surface at what angle? At an angle of 50 degrees. Right. And the ray travels from water, whose refractive index is 4/3, to glass, that is 3/2, 1.5. Yeah, 3/2. Now they are asking, find the angle of refraction. What is so tough about it? It's just one step and you people are still doing it. 4/3 into sine 50 is equal to 3/2 into sine r. 8/9 times sine 50 is equal to sine r. R will be sine inverse of 8/9 times sine 50 degrees. Okay, so this will be the final answer. Now do 13th problem. Do it faster. Tell me in terms of sine inverse. I don't want it in terms of angles at all. 2 minutes time. What is the answer? What's the answer, guys? Sine inverse of 0.45. How did you get that?
Yes, sir. Sine inverse of 60 by 133.
Ah, sir. 60 by 133. I got it.
Even getting 60 by 130.
1.2 into sine 30 is equal to 1.33 into sine r. So 0.6 is equal to 1.33 times sine r. So sine r is equal to 60 divided by 133. Okay. Next one you need not do. Okay. So refraction with respect to plane boundary is over. The next heading that you can write down is refraction at spherical surface. Okay. So next one that you're going to write is refraction at spherical surface. If you have a spherical surface like this, okay. So till now we had the boundaries which were planar in nature. Now you have a spherical surface. So with respect to the spherical surface, what will happen is, let's say it is separating a medium of mu1 and mu2. Okay. This spherical surface will have the center of curvature somewhere over here. Okay. Now, let us consider a point object placed here so that if I take this as the rarer medium and this as the denser medium, there will be a ray which is traveling and hitting this surface. So this is the incident ray. At this point, what will happen? If you draw a normal like this, okay, if you draw a normal like this, then this will be the angle of incidence. And the ray keeps traveling like this. That should have been the actual path. But since the ray is traveling from rarer to denser medium, what will happen? The ray will start bending towards the normal. And this is one of the refracted rays. Okay. There will be another ray that you can consider along the axis itself. Then this will go undeviated. So when it is going undeviated, then this is the point where the image is formed. So what we can say is this distance is the image distance, this distance is the radius, and this distance is the object distance. Okay. So if I take this angle as alpha, this angle as beta, and this angle as gamma, okay, I'll not call it gamma, rather I'll call it as theta. Okay. Then if this is the angle of incidence, then this is the angle of refraction. Am I clear till this point?
Yes, sir.
Okay. Listen to this clearly. Now our job is to derive the relation between the refractive indices mu1 and mu2 in terms of u, v, and r. Okay. So, how we can do is mu1 into sine I is equal to mu2 into sine r. Okay. Here, an important note to be made is, I told you all the angles are small. So all the angles are small, then what will happen? Sine of that angle can be approximated to the angle itself. So mu1 into sine I is equal to mu2 into sine r, which implies mu1 into I is equal to mu2 into r. Let this be equation number 1. Okay. Now, if this point is O, if I take this as A, then observe, if I consider the triangle A, O, and B, if this angle is beta, this angle is alpha, this angle is I, what is the relation between all the three parameters? What is the relation between all the three angles? You look at the triangle, you know the basics of geometry. What is the relation between all the three angles is what I asked. We'll do one thing, I'll see you all tomorrow. We'll wind up.